Hello everybody. In this video we're going to talk about a topic that we visited before, which is the absorption, the gas absorption, but in this video we are going to start discussing it in a different system. So we talked before about the absorption in tray columns, and we saw how we can use the graphical method to calculate the number of stages required to achieve a specific absorption of a gas from a gas mixture. But in this case, we want to see how we can do this in a packed column. The nature of the two systems is different, and that's why the governing equations and the way of calculation is different. And this is what I'm going to do in the next, or in this video and the coming videos. So I think I'm going to make two videos for discussing the theoretical background, because it's important. At least from my point of view, that it's important for whoever gonna do these calculations to understand first why it's different from the tray column, and second is how we reach the final form. At the end, we'll reach a form and some kind of systematic steps that we're gonna follow, and that's all. But it's important to know how we reach at this point, how we came to know that this is how we're going to solve the problems of the packed columns, or calculate the height of a packed column. So the first point is to understand what's the difference between the tray column and packed column. So this is what people call people call the stage-wise contact versus the continuous contact. So stage-wise contact is what we did before, that we have stages, and for each stage we have a contact between gas and liquid, and this contact results in like this foam that happens, which offers a very large area of mass transfer, and where the mass transfer takes place, and then the gas goes to a next tray in the above, and then the liquid goes to the tray below, and that's how the mass transfer takes place. In case like this, we know exactly where mass transfer takes place. We know it takes place here and on each stage, and I know that between the stages nothing happens, and it only happens here. And I can tell from the inlet liquid flow rate and the inlet gas flow rate, I can easily tell how far I am from the equilibrium compositions, and the maximum separation that I can achieve in each stage. And that's why we can easily, it's not easily, but we can tell how many stages, or we can call the ideal stages that we can use, so that we can achieve the required separation. Or in case I want to go for actual stages, I can assume an efficiency, and using this efficiency I can tell what is the actual separation that's taking place, and the actual compositions of the liquids and the vapor leaving the stage. So this is how the calculations were going in this case, and as you see in this case, I just wanted to know the equilibrium relation. I didn't want to know anything related to the kinetics of mass transfer, or the rate of mass transfer, or the I'm sorry about that, or the I'm sorry, I don't want to know anything about the rate of mass transfer, or the flux, or the mass transfer coefficient, or anything related to this. I know where I am at the operating line. I know the equilibrium curve. That's all what I need to do, or I need to know to do the calculations. On the other hand, in the continuous contact, the system is totally different, because in this case I have liquid contacting vapor continuously, and that's why it's called continuous contact. In this continuous contact, I have the contact continuously between the liquid and the vapor, so that in each millimeter of the column, or of the packing that I am using, I have mass transfer taking place between the two phases. So I cannot do the calculations based on the assumption of stages, because I don't have stages here. I have a continuous contact between the two phases, and in each segment of this column, I have difference or change in the composition in the liquid and in the vapor phase, and that's why I can never use the equations, or the method of the calculation that I did in the tray column, or in the stage-wise contact systems. So that's why in this case I will need to know information that I was not concerned with when I worked with the tray column. By this information, I mean the rate of mass transfer, which will include the knowledge of the mass transfer coefficient and many other things. So in this case, the calculations will be different. And this is, as you can imagine, or you can conclude from what I said, that this is a distributed parameter system, which means it's kind of, in a sense or another, like the plug flow reactor, where you have the composition changing at each segment of the reactor, and this is exactly what happens here. So you can expect that for cases like these, you will do the governing equation on a segment or a differential part of it, and then we will integrate over the whole length of the column. And this is what we're going to do. So just to be kind of expecting what you would see and why we will expect this kind of equations to solve at the end of the day. So what I'm going to do now is I'm going to go for like a quick revision on some of the concepts of mass transfer, because it's important to have this in mind. And I know they might not be present in your mind, or you need some refreshment. So I thought it's a good idea to go for like this video to do this review on these concepts. I'm not gonna go in deep. I'm not gonna go for like the basics of the basics. I'm gonna go for the parts that will be of concern to us in this system. And I followed the like the procedure, or the method that was discussed in this textbook, which is Transport Processes and Separation Process Principles by Christie and Coppolis in the 4th edition. It's a very nice book, and its language is simple and it's easy to follow. But what's said here is going to be almost the same that's said in any mass transfer textbook, because it's the basics, and nobody would say something different in this part specifically. But what I want to highlight here is that I'm following the textbook with the notations and with the symbols that they are used in the textbook. So they might be different from another textbook, I'm not sure, but in case you want to check any of the symbols that I didn't mention, please go to this textbook, and there are more details if you are interested that you can find there. So we're going to talk about the mass transfer by convection. Of course, we know that mass transfer takes place either by diffusion or by convection, and in this case we're going to talk about the convection, because this is the method that we always face in the mass transfer processes, like the distillation, like absorption, and all these things. So there are cases where we have what we call the equimolar counter diffusion, which is the case of distillation. We have a component leaving the liquid phase, which is the more volatile component, to the gas phase, and in the same time another component is leaving the gas phase and diffusing into the liquid phase. So we have counter diffusion in both sides, and that's why we will see that there is the concentration and partial pressure profiles. This is the more volatile, or the less volatile component, that has higher concentration in the bulk of the gas, and then it has lower concentration in the interface. There is an equilibrium at the interface between the concentration in the liquid phase and the partial pressure in the gas phase. So these two are in equilibrium with each other. And finally, we will end up with the concentration in the bulk, which is less than the concentration at the interface. And we must have this difference so that we can have a driving force to force the component to go from this side into this side. And the other way is for the more volatile component. It's higher concentration here and lower concentration here, and we have the same profile. So this is the first case. The other case, or the second case, which is the case of absorption, which is A diffusing through stagnant or non-diffusing B. So we have a liquid phase, maybe water, and then we have a gas phase that contains sulfur dioxide, contains ammonia, contains whatever the component that we want to absorb, and then the diffusion takes place, or the mass transfer takes place, only in one direction, where the species transfers from the gas phase into the liquid phase, and we will have only one concentration profile, as we see here. So these are the two cases that we face. For the two cases, we will have the mass transfer equation that describes it. The convection mass transfer equation is the same. We will have a mass transfer coefficient multiplied by the driving force. So of course, this is the flux, it's not the rate. The flux, which is the rate divided by the cross-sectional area. So if you want to get the rate, then we will multiply the NA by the cross-sectional area or the area of mass transfer, whatever the area of mass transfer is. So in this case, we will have K multiplied by Kp multiplied by difference in partial pressure, or we can call it Ky if we multiply by the mole fraction difference. Both are mass transfer coefficient, only the difference, of course, the values are different, but the main difference is in the units, because this has the units that will end up after multiplying it with the driving force to be equal to the units of flux, and the same for Kp. The same for the liquid phase. We have either Kc multiplied by concentration difference or Kx multiplied by the mole fraction difference in the liquid phase. Keep in mind that we have dashes here for the four mass transfer coefficients, and this dash indicates that this is the mass transfer coefficient for the equimolar counter diffusion case. Just to differentiate between this case and the other case. So for the other case, we will have almost the same equations, but without having dashes here for either Kp, Ky, Kx, or Kc. None of them has the the dash there. So there is a relation that can relate the mass transfer for counter diffusion to the mass transfer for the equimolar diffusion. I mean the equimolar to the unidirectional mass transfer, which is this Kc equal Kc dash divided by xbm, and Kp equal Kp dash divided by ybm. So this can be applied for Kc and Kx, and this applied for Kp or Ky. It doesn't matter. So in this case, we have the xbm and ybm. So in this case, we assume that the component that's diffusing, it's called component A. This is the component that's diffusing, and the other component that's stagnant here, that's not diffusing, is called component B. And this is the xbm, which is the logarithmic mean of the concentration of component B in the liquid phase. So this is, it's going to be X A interface, and this is X A at the bulk. And from this we can calculate the xb, which is 1 minus xa. So this is going to be xb interface, which is concentration of B at the interface, the concentration of B in the bulk, and this is the logarithmic mean of these two components. xb, as I said, is going to be 1 minus xa, assuming we have only two components. So this is 1 minus xai minus 1 minus xa divided by ln this over this. So this is the logarithmic mean for xbm, and this is the ybm. And again, keep in mind, this is the other component. It's not the component that's diffusing. Where did we get this from? There is a derivation for this in the textbook. You can get back to the textbook and revise it if you are interested. But this, I can assure you that this is right. It has been proven for a long time. So now we can rewrite this equation in the terms of the K dash, which is K dash Y divided by YBM multiplied by the Y driving force, or K dash X divided by XBM multiplied by the X driving force. By rearranging this equation, we can find that it looks like this, which is YA minus YA interface divided by XA minus XA interface equal these things. This is, of course, you know that this is the straight line equation. So we can graphically represent this by the on the graph of y versus x. We have 2 points, YA and XA, and YAI and XAI. I know YAI and XAI are in case of equilibrium, or in a state of equilibrium. So the second point should be on the equilibrium curve. And this is a straight line equation, so the slope is this. This is the slope of this line. Why I'm doing this? Because this is something that we will do in the calculations of the packed column. This is one step that we will follow, and it's important for you to understand these details, because it's going to be one of the kind of tricky parts of the solution. So I'm kind of focusing here so that you understand what's going on. So there are a couple of things that you need to keep your mind keep in your mind while doing these calculations. First, that this is the equilibrium concentration between x and y, and you have to make sure or to keep in mind that the y at the bulk is higher than y at the interface, and x at the interface is higher than the x in the bulk. And this is what you can see here. This is something that you can double check, that this is the x at the bulk, which is smaller value, and then the x at the interface is larger than the x in the bulk. On the other hand, if you go from down to up, then you will have YA interface smaller than the YA at the bulk. So this has smaller value than this. So this agrees with what we have, and the slope is negative, and this agrees with what we have here. So this is important to have kind of physical or understanding of the physical meaning of the equation, and how this makes sense from what we have from the equations. So now let's say I want to calculate the interfacial concentrations. I know the bulk composition for the gas phase and for the liquid phase, and I want to know what is the concentration at the interface. So to calculate it, it might kind of seem that this is easy. I know a point here, and I can calculate the slope, and then from the slope and the point I can get the other point, but it's not as easy as it seems, because the Y interface and the X interface are here. And they are here as well. If you go back to the previous slide, you'd see that the X interface is here, Y interface is here for XBM and for YBM. So it's not that straightforward. You will have it here, and you will have the X interface and Y interface might be affecting the mass transfer coefficients. They're not always constant. So this thing is not always constant. So to be able to calculate the interfacial compositions, you have to do it by trial and error. You have to assume a value, and then from the assumed value you can do some trials until you reach a value that satisfies this equation. This is going to be one of the steps of the solution. It's kind of tricky, I know, but this is something that you have to keep in mind, that we will go through when we go into the solution, inshallah. So the last thing I'm going to mention in this video is regarding the mass transfer coefficient, or how we can calculate it. The mass transfer coefficient is dependent on almost all the parameters that are affecting the system. It's function of the fluid properties, its density, viscosity, the diffusivity of the component in the other. It depends on the flow properties of the velocity, of the degree of turbulence, and it's function of the geometry of the flow. Either it's going in a pipe or a tube, or like a porous medium or whatever. So it changes different. I mean, a lot with different systems. So from the mass transfer basics, we all know that there are some dimensionless parameters that we use to kind of make life easier for us. So instead of studying all these parameters, we study the effect of only 2 or 3 parameters here. So we have Reynolds number, that is the function of the flow properties and the fluid properties. It has the velocity, the characteristic length of the density, the viscosity. We have the Schmidt number, which is function of the density and viscosity and the diffusivity. We have here the Sherwood number, which has the mass transfer coefficient, the diffusivity, and the characteristic length. So we know that Sherwood number is a function of these two guys, or the Reynolds number and Schmidt number, and there are many equations that were developed for different systems. For each system, you have a relation between Sherwood number, Reynolds number, and Schmidt number, and from this relation you can calculate the Sherwood number, and from Sherwood number you can calculate the mass transfer coefficient. It's a tough process. I know it's not easy, but this is something that people used for a long time. One thing that you have to notice here is that the K that we have here has a dash on it. It's K dash. It's not just K. So it's the K for the equimolar counter diffusion. It's not for the unidirectional. So in case of an absorption, like the case we are using here, we have to use the K, which doesn't have the dash, as we know. But for the equations that we have, they all are predicted or predicting the value of the K dash. So we will use K dash in all our equations, and that's why we will have the like this equation that we mentioned here. That we have it as a function of K dash, not function of K, and that's why we'll have the logarithmic mean in our calculations. This is gonna be a part of the solution, so we don't have another choice. That's why what I'm saying is that's why we will use the K dash for the case of absorption, which is based on the K, not the K dash. there are some equations that are predicted or developed empirically. So some people have their system and they did a lot of experiments on the system. They knew that this is function of mainly on the let's say they have a system of water and SO2, and they did the experiments on the system many times, and they knew that this is function of mainly the flow rates, and they can predict the value of the mass transfer coefficient kind of accurately with an empirical equation based on some experimental data without going into the theoretical background. So this is one other option that we can use to predict the mass transfer coefficient. So I'll end this video now. In the next video, inshallah, we will see the equations that describe the packed bed column, and we will see how or what are the calculation steps that we are going to follow when we use Microsoft Excel, inshallah. So I'll see you then. Goodbye.